And I realize people here have very different backgrounds. I am a physicist, so to me, quantum mechanics is something I think about all the time, and topology a little bit less. I realize there are other people in the opposite situation. So I will try to explain things as I go along, but please stop me or ask a question if I introduce something without defining it well enough, etc. So the basic idea is that if you just look at one electron moving in a solid and think about its wave function carefully using some topological concepts, you can explain a number of amazing experiments. And this has been about a 30-year project in the theory of solids, but a lot has been happening in the last decade or so. And there are various ways to approach the topology of electrons in solids. There's one way I like, because it kind of ties some things together, which is in terms of the Berry phase, and I'll define what I mean by that. And one nice thing is, in addition to explaining what we call topological phases of electrons, you also explain various other things about solids that are interesting, even if they're not as topological. But the new topological phases, and I understood you might have had a talk in this series by Charlie Kane, so I will give a different way of looking at these things. The integer quantum Hall effect and topological insulators are kind of the original topological phases of electrons. Something we now understand is that there are topological effects in metals as well. In insulators, it's kind of obvious how you get something topological, and I'll explain what I mean. Basically, you're looking at a closed manifold. For open manifolds, like filling only part of the Brillouin zone, which is what happens in a metal. Yeah.
Is there an impressionistic definition of the phrase topological state of matter?
We will come to it, I promise. And so ask me in 8 slides if I haven't done it. OK, so yeah, there are about 4 definitions I know, but I'll give one which is motivated by what you actually measure. Anyway, so we think that there are things like this that happen in metals, and in particular, just in the last 3 years, we have the first solids where we think the low energy description of the electrons is as free Weyl or Dirac fermions, and I'll explain what those are. So this is basically things I'm going to talk about. So if you don't recognize words here, that's OK. An impressionistic definition of a topological state would be something where some property we care about is insensitive to smooth deformations, like if I slightly change the material or whatever. But that has consequences that are more surprising than that statement. And then finally, I thought I would touch a little bit with current matter. So the last part of my abstract was down here. I don't think I'm going to get to it, but I will hope to define what is a Majorana fermion. Basically, Weyl fermions and Majorana fermions are 2 different ways of taking half of the Dirac equation in 3D. We think we've found Weyl materials, and we're very actively looking for Majorana materials, which would be even more interesting. So the basic thing that happened in 1980, essentially we had a picture of what kinds of order exist in solids and also other things. And topological order is a totally different kind of order that we were forced to think about because of experiments. So until 1980, let me give you our standard picture of order, which topological order is not. The way we think about most order, kind of the bread and butter of a graduate education in condensed matter physics, is something called symmetry breaking. And the idea is, if I took something like this crystal and zoomed in, I would get a lattice of carbon atoms, which is quite a good lattice. It can be about 1 million atoms in any direction without a defect. And this lattice has a lot of symmetries. It has a lot of rotations and a lot of translations. But it has fewer symmetries than the vacuum, in that the vacuum has a continuous group of symmetries, while this has some discrete subset. So we could classify crystals by which symmetries of the vacuum were broken. We can do the same thing for so-called liquid crystals, like what's in a computer display, for magnets, even for superfluids, which are kind of a quantum mechanical sort of symmetry breaking. And this is more than just philosophy. It actually leads to a lot of amazing predictions about phase transitions, like when you form these phases, interesting stuff happens. But this is what topological order is not. And this was the serendipitous experiment that led people to realize that something weird must be going on. So if you have a chunk of solid with electrons in it, one of the basic measurements you do is something called the Hall effect, which goes back to the 1890s. You basically take your chunk of material, you put on a magnetic field, and you run a current perpendicular to the magnetic field. And the effect of the magnetic field is to bend the electrons. And by how much you bend the electrons, you can figure out how many charge carriers there were, either electrons or holes, which are like electrons but with opposite charge, and whether they're electrons or holes. And the way that works is normally you see a smooth dependence on the magnetic field of the so-called Hall or off-diagonal resistance. So this is kind of the classical Hall effect, and it's a common measurement. And people around 1980 started doing this on two-dimensional electron gases, where the quantum state of the electrons in the third direction is essentially fixed. So they have no motion in the third direction. They only move in the plane perpendicular to which the field is applied. And what you see are these plateaus. And if you work out what is the conductance on one of these plateaus, so let me take 1 over that, you find that it's an integer times e squared over h, where this is the bare electron charge, and this is Planck's constant, kind of the fundamental number of quantum mechanics. And the reason why this was a surprise, first, this is good to about a part in a billion. And for a few years, this was actually our best way of measuring this ratio. There's another measurement in solids that gives you E over h, the Josephson effect. So if you combine those two, you got a measurement of electron charge and Planck's constant that was as good as anything else we had. And the reason why that was surprising is that this is not some one atom in a perfect high vacuum or something. This is a big chunk of material with defects, and because it's at finite temperature, it's kind of jiggling. There's nothing perfect about the material, and yet you get some kind of emergent perfection from the way quantum mechanics works. And this was our first example of what we now call topological order. Topological in the sense that what I measure, it doesn't care about what material. I could do this in gallium arsenide or indium arsenide or whatever, or graphene nowadays. Any material where I can make a two-dimensional electron gas, I measure this and I get the same number. And it's insensitive, at least up to some non-zero strength of the defects and the thermal fluctuations and all that. So that was a surprise. This experiment has led to 2 Nobel Prizes. And let me sketch how we understand that in terms of something topological. And there are different ways. It turns out that the way I'm going to sketch was figured out in the early 80s, but it wasn't really the mainstream way of describing this effect. It wasn't in the textbooks, et cetera. But it turns out to be the best way to understand the new discoveries in the last 10 years. And it's a picture due to Thales, and let me make a mathematical analogy, which is a little oversimplified, but just to kind of sketch where we're going to go. So one topological invariant we all know is the one that appears in the Gauss-Bonnet theorem. So much of the topology that appears in physics, and including in this electronic case, you get by integrating something that has a local meaning, and that local meaning might itself be interesting, even if it's more geometric than topological. So as a simple example, if I take two-dimensional surfaces in three-dimensional space, at every point there are 2 radii of curvature, and the Gaussian curvature is 1 over the product of the radii of curvature with a sign where, say for a sphere, both curvatures have the same sense. They're either both toward me or away from me, so I call that positive curvature, while this hyperboloid would have negative curvature. So as I think some of you know better than I do, if I integrate this over a closed 2-manifold, and I'm always going to be making physics assumptions of kind of smoothness and so on, probably stronger than are actually necessary. So this has surface area 4 pi r squared. The curvature is 1 over r squared. When I do that integral, I get 4 pi. And the magic, as you know, is that however I smoothly distort that sphere, I will still get 4 pi. It's not just independent of the radius. It's kind of independent of the detailed geometry. But it does depend on the topology in the sense that if I took the torus, there'd be negative curvature here, positive curvature there. They cancel out. So in physics language, the way we'd put it is that the integral of the curvature over the whole 2-manifold is quantized. And this is the kind of topology that we're now going to apply to electrons in solids. And the first example was that integer quantum Hall effect of 2-dimensional electrons. So here's your crash course on quantum mechanics and solid-state physics. Basically, for now, let's think of an electron as a complex valued function, and we're going to think about energy eigenstates. So these are stationary states. They don't involve in time, so it's just a complex valued function of space. And the content of the first big theorem you learn in a solid-state physics class is that if you put electrons in a periodic potential, so let's say I've got 1 electron moving through the potential created by all these nuclei, then its wave function is almost like an electron in free space. It has a part that's a plane wave. This e to the ikr would be the wave function of electron in free space. And then it's got another part which is periodic with the periodicity of the unit cell of the crystal. And often we kind of ignore this u sub k, but it's going to be the hero today. And k is defined on a d-dimensional torus, which we call the first Brillouin zone. So think of k as just a square or a cube with periodic boundary conditions, if you like. And if you want to know what the difference is between metals and insulators, Well, a lot of a solid state course typically focuses on how does the energy depend on crystal momentum. And you get continuous dependences, but there are usually several discrete levels or bands. And if you have a partially filled band, that's a metal. If all your bands are completely filled or completely empty, that's an insulator. So I've got some functions. E1 of k would be the lowest electron state. E2 of k will be some other function, the next excited state. And depending on whether I've filled some and emptied the others, that's an insulator. If I've partially filled at least one, that's a metal. So now you don't need to take solid state if you never bothered taking it. So the Brillouin zone, which is the d-dimensional torus of inequivalent values of momentum in this equation, that's going to be the surface I use to make my integrals. So our manifold, in a sense, is fixed, but what makes one solid different from another is that there's a different kind of bundle structure of wave functions on that manifold. And we're going to use those wave functions, these things, to make a curvature analog, which in physics we call the Berry phase usually. Let me sketch where that comes from. And effectively, this is a gauge field just like the gauge fields in particle physics, but it's particularly simple in a way. We don't really need to think about its dynamics most of the time. If you give me the crystal, I know the wave functions, and those depend on this momentum k. If I have wave functions that depend smoothly on a parameter, there's a natural sort of holonomy to think about. And the way we typically write it in simplicity, in simple physics language, is there's a Berry phase if I take my parameter around a closed path in parameter space. So for me, my parameter is going to be momentum. And the way we write the Berry phase is like the integral of a vector potential in physics language. Let me explain why we write it this way in the next slide. But just to define it, at least assuming for the moment that I can define my wave function smoothly as a function of the parameter, then the way I define this A is that if you give me a wave function at each point in parameter space, and let me assume for the moment that my wave functions are non-degenerate in the sense there's only one wave function I have to worry about at each point in k-space, then if I take its derivative in the following way, that gives me an object, a connection, that turns out to be very useful in solid-state physics and in some other contexts as well. So this would be the first thing that Berry thought about, was just loop integrals of A. But let me try to justify why did I write it this way, and could this really be a physical quantity? It turns out that A directly is not a physical quantity because of a nice property of quantum mechanics, but there are things we can make out of A that are physical. And if you want, the way Berry originally motivated all this was thinking about adiabatic processes in quantum mechanics. Adiabatic means I smoothly change the Hamiltonian as a function of some parameters, but that's not really necessary. In fact, that's not what I'm going to talk about, but it's the same mathematical structure. So I've got a wave function that's changing adiabatically with the momenta, but it's not adiabatically in time. It's just some smooth change. So here is sort of the mathematics of why this is an interesting quantity. So in quantum mechanics, I said I'm dealing with complex valued functions of space for my problem. If I change those by an overall phase, that's not actually measurable. So there's kind of a U1 ambiguity in the sense I can change my phase by a phase factor. And in particular, for the problem I'm talking about, where I've got wave functions that depend on this parameter k, I might choose psi sub k, and you might choose a different phase convention. So some different phase that varies with k. And physics should not depend on this. This is like a gauge choice in gauge language. So if I make this change, then the vector potential changes by a gradient of the phase factor. And that's actually just like the vector potential in electrodynamics. Classical electrodynamics is the simplest example of a U1 gauge theory of this type. So that's a clue because it tells us things we can make out of A that are gauge invariant and might be physical. The simplest one is curl of A. And if you want a slightly better way from a mathematical point of view to write the curl of A is to think about here I had to introduce a gauge-dependent object in order to extract a gauge-independent quantity. It's kind of easy to see that this is independent because that gradient drops out. If you would like to be, for this quantity at least, you can actually write it in terms of the projection operator, which is a gauge-invariant object. So you don't have to work with gauge-dependent objects if you don't want to. But for some other cases, we do actually need gauge-dependent objects. And one immediate generalization for which the first physical consequence was just worked out a few years ago is that if instead of having just one wave, P is the projection operator onto my wave function. So the idea is that if I take this Ket-Bra combination, that cancels out the phase choice. So it's some index of a projection operator, I guess would be the way to put it, is a different way to get this F. So the non-abelian case is the following. If you know your particle physics, you know that electrodynamics is a U1 gauge theory, which means it's abelian in the sense that these phase factors commute. But the other forces in nature, at least the ones we understand, the strong and weak forces, are non-abelian gauge theories. There are non-abelian gauge fields in solids. There are many cases where either two bands come together, which means I've got a degenerate set of states, or more commonly, they don't actually come together, but some physical processes don't care about the energy difference between them. And in that case, I have some upper indices which label some basis in that degenerate subspace. And this is the non-abelian version. So now A has both a spatial direction in parameter space and these upper indices. And I'll come back to this a bit later on, but the good thing is for plenty of simple phases, we don't need to worry about the non-abelian connection. The abelian-Berry connection is enough. And then if you want to kind of work out an example where this is easy to picture, the example that Berry used in his adiabatic version was just think about a magnetic field that couples to the spin of an electron. And I'll define spin later on. I guess I did this out of order. But anyway, if I've got a Hamiltonian of this type, so some magnetic field where the only thing changing in time is the direction of the magnetic field, and that's coupling to the spin. So spin in this case is a Hilbert space of dimension 2. It's the simplest non-trivial Hilbert space we can have. So this is coupling to basically the Pauli matrices acting in that two-dimensional Hilbert space. Then the Berry phase I generate by taking this around a path in parameter space, I can represent as just the area enclosed by this vector n trajectory on the sphere. So that's one example of how to connect sort of topology to the Hamiltonian, or what the Hamiltonian did to what the wave functions are doing. Okay, so now back to solids. I said F might be physical because it's gauge invariant. And the first dramatic example of that was what explained the integer quantum Hall measurement I talked about. So if you remember, the idea was that if I measure this two-dimensional electron gas, then I see an integer times e squared over h in the transverse conductance. And the way that happens, so this is just writing out integral of F in terms of the wave function. If I sum over all the occupied bands in an insulator, it turns out each one of these, each band has a Chern number, which in physics we sometimes call tk and n integer. Basically, the first Chern number is some integer that that band will have. And that's physical in the sense that the Chern number of this U1 bundle on each band tells me just how much will that band contribute to the quantum Hall effect if it's filled with electrons. So this was maybe the first kind of topological understanding of electrons of the type I'm going to focus on, that some kind of topological invariant in energy bands of two-dimensional materials is measurable. And this kind of explains why this is so robust, because if I make a little bit of a change in the material or something, this is an integer. It's topologically quantized in our language. It's not going to jump to some other integer. So that explains at least partly why this is so stable, without getting into the physics details. So as far as physical consequences, or another kind of interesting thing about what does this topological invariant of the bulk mean, and how do you connect it to actual observables? And this is kind of important for how some of the new materials were discovered. So if you're wondering, what I said before was that an insulator is something where bands are completely filled or completely empty. So completely filled or completely empty is a requirement for this to be an integer. But then if it's an insulator, here I'm saying it's conducting charge. So what's conducting charge if it's an insulator? That sounds like a contradiction. And one way that can happen, there are different ways that can happen, actually, but the simplest one is the following. What's going on is that topological invariant means my wave functions are kind of topologically non-trivial in the middle of my two-dimensional electron gas. If I go out into vacuum or an ordinary material, then all those Chern numbers are 0 and things are kind of topologically trivial. And at the boundary, something discontinuous happens, and that discontinuity in physics is there's a metallic boundary. So the statement is, if I've got a topological phase of this type, whenever I put it next to an ordinary insulator, then there is a metallic boundary. And in fact, that metallic boundary in the quantum Hall case is very simple, but it's a little bit bizarre if you're used to thinking about ordinary wires and all that. It's a one-dimensional wire that only has electrons moving in one direction, so we call it chiral. And the sort of very rough picture of the words I just gave you is that in a topological phase, the wave functions are topologically non-trivial, like this trefoil knot. Outside they're trivial, something discontinuous has to happen, and the physical meaning of the discontinuity is usually that there's some metallic region in between, and you have to think more carefully to justify this and figure out what exactly is the metallic region in between, but that's a way you could actually look for topological phases. If you can find materials where they're insulators, but wherever you make a boundary, there's something conducting, especially if it's a weird kind of conductor, that's a clue that there's something topological about the wave functions in the bulk, and that's how the first 3D topological phase that I'll come to was found experimentally. So just to kind of map out other cases where this concept is useful, and I promise I will not cover all of these in the talk, but basically what we just talked about in the two-dimensional quantum Hall effect, which has a four-dimensional version based on the second Chern number, is a topological phase where I didn't really need to think about symmetry. I just said, you give me my electronic wave functions, I calculate something, and that tells me if I'm in the trivial phase or the topological phase. When you add symmetry, the topology gets kind of richer, and that was maybe the beginning of kind of this new era in the last 10 years or so, because it turns out that to see the quantum Hall effect, you need large magnetic fields and low temperature, and it's not that easy a thing to do. There are some materials that just sitting there by themselves are actually in a topological phase, and we can measure that, and I want to explain what those are, and that will be a slightly different explanation of what I think Charlie Kane probably told you about if you were at his talk previously. So there are various other things. The first non-abelian topological consequence is something called the magnetoelectric effect. I want to sketch that. And then just to present something that we and other people are working on now, even in metals, it turns out there's some things that are topological. And the first experimental examples of that were kind of found in the last couple of years. So I should say that because I'm giving sort of an overview, there are things that I've worked on here, but a lot of what I'm talking about is definitely work of other people. And I'll try to credit it. But if I forget, don't necessarily assume that everything I say is stuff that I did. So the reason for presenting this kind of topological invariant of my electrons in a solid in this way is that we can generalize it to 3 dimensions. It turns out that the physics is different, but the mathematics is very similar in spirit. There's something I can calculate about these electronic wave functions in a 3-dimensional material that will tell me if it's topological or not. And if it's topological, there will be some kind of edge or surface state at a boundary to an ordinary insulator or vacuum. So if you want, we've already seen kind of 2 definitions at least of what a topological phase is. One is that something I can measure is given by a topological invariant. Another is that most topological phases, at least the ones we clearly have in experiment, have this property that the bulk might be insulating and inert, but there's always some kind of boundary state. And then a somewhat more formal definition is that the kind of field theory that is sort of the effective or abstract description of these is a topological field theory in the sense of Witten, rather than a conventional metric-dependent field theory, which is the way symmetry breaking phases are described. So anyway, the physics is different, the experiments are different, and it can occur in 2 and 3 dimensions. Let me sketch how these new topological insulators work, and then I'll mention some mathematics. So the one thing we need to add is electron spin. And the basic idea is that the electron is almost as simple as you could imagine. It's not quite a complex valued function of space-time. It's 2 complex valued functions of space-time because the electron has spin half. Electrons are spin up or spin down or some arbitrary superposition of up and down. The fact that they're spin half is important because spin half particles prevent other identical particles from occupying the same state. They have so-called Pauli exclusion, while integer spin particles do not. So basically there's an enormous difference. Maybe the most fundamental difference in nature maybe is between integer spin particles, which I can pack an arbitrary number into the same state, like photons in a laser, and half-integer spin particles, which can't go into the same states. They kind of have to stack up in energy, which is why the periodic table works the way it does. So we'll come back to that difference between integer spin and half-integer spin, because the mathematics of how that works was actually the key to figuring out topological insulators. So the basic discovery is that it's been known that electrons have spins since the 30s, but something interesting happens in materials where the spin of the electron is strongly coupled to its motion around an atom. which is called spin-orbit coupling. And that's especially strong when the electrons are moving close to the speed of light, which is what happens in heavy elements toward the bottom of the periodic table. So if you want a quick idea of why there is spin-orbit coupling, the idea is that, well, in the rest frame of the nucleus, there's a strong electric field. An electron moving rapidly through that electric field sees it partly as a magnetic field because of special relativity, and that effective magnetic field couples to the spin because that's what spins do. Spins are associated with magnetic moments. It's just that they aren't really the magnetic moment from a current flowing through space. Even a point particle, we think, has a magnetic moment because of spin. And that was very mysterious in the early days of quantum mechanics, and maybe even still a little bit mysterious now. So the original topological insulator was really explained by Kane and Mealy at Penn. And here is a sketch of where it comes from and how it's related to the quantum Hall effect. And it will lead to a different kind of topological invariant. Instead of an integer, it'll be a Z2 invariant in the sense that there are only two possibilities. And let me come to that in a second. But where it comes from physically, spin-orbit coupling, in the simplest case, I can write as a dot product between the spin of the electron, so it has some axis around which it's spinning either right or left, clockwise or counterclockwise, I should say, and then its orbital angular momentum, which is the angular momentum of how it moves through space. If you take this and you write out what this looks like in terms of wave functions, say, this is a lot like a magnetic field in that this is r cross, well, space cross momentum. This is like a momentum-dependent force, basically, but it's a force that's one way for spin up and the other way for spin down. That means it's like a magnetic field that's one way for spin up and one way for spin down. So what people had kind of imagined without much justification, because they didn't understand the topology, was that maybe you have a material that just sitting there has spin-orbit coupling, so no applied magnetic field. Then maybe the effect of the spin-orbit coupling is to make two copies of the integer quantum Hall effect, where electrons that are rotating one way along some axis go along the edge, say this way. Electrons that are rotating the other way go there. And until 2005, no one took this very seriously, because basically we didn't see any reason why this would be stable. We thought that if we turned on some real disorder or anything like that, these will kind of mix with each other. You can sort of see why this is stable, because if there are only electrons going one way, there's nothing for them to backscatter into at low energy. So basically, physicists had good reasons to understand why this was a stable state of matter, and we did not understand why that was stable until the topology, which was this Kane and Mealy paper, actually two papers in 2005. So yeah, I won't go into the details of why we didn't believe it, because now we do believe it. What they found was basically all those integers I talked about before, all the Chern numbers are actually 0 if I just have a non-magnetic material sitting there. There's a symmetry that forces them to be 0. But if I have a non-magnetic, or more precisely, time reversal invariant system sitting there, then there are still two possibilities, ordinary insulator or topological insulator in 2 dimensions. So I want to kind of explain what is it about electrons that leads to this Z2 distinction, and how can you see it? How you can see it is basically to try to measure whether or not there's a gapless edge. But why is there an odd-even effect? That was the big surprise, maybe. So here's a simplified picture, because I think you've probably heard the original picture from Charlie, maybe. So you have to go back to the early days of quantum mechanics and someone named Kramers, who was kind of a buddy in the Netherlands of Loschmidt and Uhlenbeck, who are the ones who figured out that electrons have spin half. So what Kramers figured out was this fundamental difference between spin half particles, and like the electron, and integer spin particles, you can view as related to the action of the time reversal operator. So you would think that if I reverse time and I reverse time again, I should get back to where I started. But in quantum mechanics, you always have this phase factor. So what actually happens is that with electrons, if I reverse time and reverse time again, it's like a rotation by 2 pi. And if you remember quantum mechanics, a rotation by 2 pi for an electron actually gives you a -1, not a +1. So there's a simple consequence of that, which is kind of profound and is what underlies all this, which is that if you have an integer spin particle, then basically, if I've got a system that has time reversal invariance, and not all systems in the universe, but most systems have time reversal invariance, then if I reverse time, I have to be at the same energy. That's what the invariance means. But there's no problem with a state being the same as its time-reversed version for integer spin particles. So you can have a non-degenerate state that is the same whether the movie is running forward or backward for integer spin. For electrons, that doesn't happen. You actually are always degenerate with, but different from, your time reversal version. So if you have an odd number of electrons in your body, say, or odd number of spin-half particles, then you would be different from your time reversal conjugate running around somewhere, but at the same energy. So those are what are called Kramers pairs, that basically non-degenerate, so you can't have a non-degenerate electron eigenstate in a time reversal symmetric system. So how does that help us understand why this is stable? Well, that's where the odd-even effect is going to come from. So I'm going to draw, and apologies for drawing physics pictures. This is energy versus momentum along the edge. So this is basically a right-moving bunch of electrons, let's say with spin up, although that doesn't matter too much, a left-moving bunch of electrons with spin down. So the idea is, I said that there are these degenerate pairs of states related by time reversal. I can't split them, at least in a time reversal invariant system. That would kind of violate my assumption. So what that means in practice is that there's actually no way to scatter an electron here to a hole there. I cannot relax a current, which is going one way along the edge, because this process is forbidden by that time reversal symmetry. If I have a normal quantum wire, in the sense of having both spin up and spin down channels going right and both spin up and spin down channels going left, that same process is still forbidden, but I can scatter between the right mover and the left mover that it's not its time reversal conjugate. So this is what we normally call a quantum wire. Like if you've heard of carbon nanotubes, those would kind of be like this. We believe that a quantum wire will be localized by disorder, in the sense that if I put on even a little bit of disorder, it'll stop conducting. But if we take half of a quantum wire, in this sense, then time reversal symmetry actually protects it. So this is kind of the odd-even effect. Odd is stable, but if I take 2 copies of odd, I get back to even. And mathematicians or mathematical physicists have made more precise versions of this, and I'll show you an incredible table that they've worked out in a second. But first, these do exist in experiment. If you make the right quantum well out of mercury cadmium telluride, you can actually see a system that has a quantum Hall-like conductance even in zero magnetic field. So it's basically a 2-dimensional square of material that conducts like one perfect quantum mechanical wire, which we think is coming from the edges. So that's the 2-dimensional quantum Hall effect. Briefly, me and many other people, we all thought this Kane and Malik paper was very interesting, so we started trying to generalize it. And one direction that we and other people went was think about higher dimensions. And what you realize is that the quantum Hall effect doesn't have a generalization to 3D, but the Z2 invariant does. And we had a very kludgy physics way of approaching this, which I'm not even going to explain. But I'm going to tell you in a moment about the incredible generalization to all dimensions and all symmetry classes worked out by Kitaev, basically, using K-theory. And I'll just flash that up because maybe, I think for mathematicians in the audience, you might find it interesting. Let me say a little bit more about the physics of the 3-dimensional topological insulator, because I'm going to use that a little bit later on. But basically, this is now a 3-dimensional insulator that, as its surface, always has a 2-dimensional metal. So in other words, you've got a chunk of material lying around. Wherever you cut it, the bulk is insulating, but it has kind of an atomically thin metallic conducting layer because the bulk electrons are wrapped. And if you zoom in on what the surface looks like, the Penn group explained what would the surface consequence be in the 3-dimensional topological phase. In the simplest case, you get sort of an effectively massless electron, in the sense E linear in K is like the mass is 0. So this is energy versus momentum at the 2-dimensional surface of a 3-dimensional material. There's kind of an interesting locking of momentum and spin, but basically there is a specific enough idea of what the surface would look like that you could tell experimentalists what to look for. And what they did, I saw that you were celebrating the 100th anniversary of general relativity soon. Einstein didn't actually win the Nobel Prize for general relativity because that was controversial. I think he mostly won for this, the photoelectric effect, which is you send in a photon, you bounce out an electron. In the old days, they could measure the energy of the electron. Now, after 100 years and $1 billion, or several $1 billion, they've gotten very good at this. You can measure the electron very carefully and figure out, before you bounced it out, what was its energy, momentum, spin, et cetera. Basically, what was it doing before you bothered it with some X-ray photon? So that's called ARPES, if you want to be cool. Angle resolved photoemission spectroscopy. And if you do that, this was maybe the smoking gun for the 3D topological insulator. So bismuth selenide is an old material that people had lying around because it's slightly useful for something. And it was known for a long time to have a band gap. It was thought to be an insulator where there was some range of energies. So this is energy and this is momentum again. There was some range of energies where there were no states in the bulk. It's this range from 0 to 0.3 eV. If you do this angle-resolved photoemission spectroscopy, you realize there are states in the bulk gap, and they're localized at the surface, and they even look a little bit like that Dirac cone shape. So this was not technically the first experiment, but the cleanest experiment that showed us that there are these three-dimensional topological insulators. And I'll say a little bit about their consequences later on, but let me mention how this led to some interesting mathematics. So mathematicians are really good, at least compared to physicists, in classifying things. You probably have heard maybe that there are 230 space groups that you can fit crystals in. If you add magnetism, there are 1,441 magnetic space groups, et cetera. If you don't care about the details of crystals, if you only care about symmetries that we think survive even when you have disorder, then we think there are only 10 classes of free electron problems you should care about. And just to explain those, the first three are sometimes called the Wigner-Dyson classes of random matrices, for example. And they're basically problems where you have broken time reversal symmetry is the class of unitary matrices. There's a class of symplectic matrices, which is basically you have time reversal symmetry of spin half particles. And then there's a class where you have perfect time reversal symmetry. In our language, we'd say there's one class where time reversal is not a symmetry. There's another class where time reversal squares to +1, and there's another class where time reversal squares to -1. So that gives you the three Wigner-Dyson classes, which are just because of time reversal. If you're wondering how you get 10, there's another symmetry which appears in superconducting materials. So basically, 3 of these are very physical, and the other 7 you have to look a bit harder for in things like superconductors. And that other symmetry, you similarly have 3 options of t squared equal to +1, t squared equal to -1, or t squared equal to 0. So obviously you get 3 times 3 equals 10. If you're wondering why it's 10 and not 9, the reason is that you could imagine a case where it's not invariant under time reversal or the superconducting symmetry, but it is invariant under the product. And if you work out the details, that gives you 1 more class. So there are actually 10. And we label them using this Cartan notation. So this is basically saying that if you give me electrons and you don't care too much about what kind of crystal they're in, there are 10 problems you'd want to solve. And the ones I've already talked about kind of appear in this table. So for example, the 2-dimensional quantum Hall effect is this one, this integer class. The 4-dimensional quantum Hall effect is this one. The topological insulators I talked about are class A2 symplectic matrices. That's Z2 in 2 dimensions and Z2 in 3 dimensions. And all these others, we have a few experimental examples of, but the main point, and this is maybe the magic of what Kitaev did, basically physicists had worked out how this worked in 1, 2, and 3 dimensions, but it took Kitaev to explain how it works in any number of dimensions. So string theorists can only go up to dimension 26, but we can go up to any dimension. So here's how it works. Basically, the right way to think of 10 is as 2 plus 8 rather than 3 plus 7. There are 2 classes where you can see there's an integer hopping back and forth. And then there are 8 classes where there's kind of a steady procession through the 8 classes. So this is, I know how to say the words. I don't exactly know what they mean. Real and complex Bott periodicity, I gather, something like that. But I guess the remarkable statement is that in every dimension of these 10 classes, 3 of them are integers and 2 of them are Z2. But which 3 are integer and which 2 are Z2 kind of processes in a predictable way through dimensions. So this is more a mathematical physics thing because we don't have examples of most of these, but it's kind of a remarkable thing. And getting to recent work,
You don't have examples?
we don't have physical experimental examples. We can kind of make, I think if we wanted to, we could make Hamiltonians or something. So when I say examples, I mean like in the lab. And actually one bit of progress on this by someone here, Ed Witten, was Shinsei Ryu, Andreas Ludwig, and I had figured out that a few of these you can sort of generalize to the interacting case. You can formulate in terms of a so-called anomaly, which is sort of a form of quantum mechanical breaking of symmetry. And we had some words that maybe the others have something to do with a much more complicated kind of anomaly. And a recent long paper by Witten is saying that those words that we had just scribbled as a guess are actually correct. So I wouldn't even dignify it by calling it a conjecture, but it is actually true, remarkably. So if you want a a new way of looking at this table. So Kitaev's was in terms of sort of K-theory classification and smooth deformability, I guess. This is a way to look at it in terms of free fermion anomalies. But yeah, it doesn't help us find experimental examples. But we do think helium-3, it turns out there's a phase of superfluid helium that we think realizes one of the superconducting classes, and we're trying to build others. I will say later on at the end, if I get to it, why the superconducting classes in this table are particularly exciting. Basically, they realize a new kind of particle that we would love to find. So even if it's hard, people are trying. So related to this anomaly thing, let me give a simple example of how you would motivate that problem. Basically, when we talk about real electrons, they aren't independent of each other. They interact with each other. So if you want to define what a phase is, you usually want to do it in some kind of response that is something you can measure, like the conductivity in the Hall effect, rather than a single electron property. And it turns out that Wilczek, thinking about a different problem, had sort of worked out what is the effective theory in terms of a response of the 3D topological insulator back in the 1980s. But in understanding why that's right, that's how you come across this non-abelian version of the Berry phase. So let me sketch how this works. Basically, what Wilczek thought about was a problem that is easy to state in undergraduate electrodynamic terms, which is we know that if we go into a solid, we modify some things about the electromagnetic response. You might think that if you go into a solid of low symmetry, you generate an interaction between the electric and magnetic fields of this type. So this happens in some materials where if you apply an electric field to the material, you measure a magnetic moment. If you apply a magnetic field, you measure an electrical polarization. That's been known for a long time, but what Wilczek realized was that basically it was thought that you needed to break both time reversal and spatial inversion symmetry for this to happen. That's not quite true. Even if you have those symmetries, there are two possibilities left, which are, in particle physics language, theta equal to 0 and theta equal to pi. So we'd kind of figured out that there were two classes of materials with time reversal symmetry in the language of this effect. And we now realize that one of those is the ordinary insulator, and one of those is the topological insulator. And I want to give a quick sketch of how that works. So before I told you about the Hall effect, which is you apply an electric field, and because there's a magnetic field, a current flows perpendicular to it. The magnetoelectric effect in bulk, E dot B, through kind of elementary calculus, is nothing different from saying that the surfaces have a Hall effect. Just to explain it, E dot B, if you write your electric and magnetic fields in terms of the field strength tensor, this is actually a total derivative. That's what E dot B is special compared to E cross B or something like that. The fact that it's a total derivative means I can basically move it to the boundary. And if I ask what is the boundary version of this, it's just the Hall effect. So in other words, if I have a material with a bulk E dot B, that's the same as saying the surfaces have a Hall effect. So for what I said before about topological insulators theta equal to pi to make sense, that would be bizarre. That would mean that the topological insulator surface doesn't have an integer Hall effect. It's not n times e squared over h, but it's a half integer times e squared over h. And we actually know that because of an experiment which has a material similar to the surface of the 3D topological insulator. So graphene is a Nobel Prize-winning discovery in solids that I'm not going to have much time to talk about, but it's a two-dimensional single layer of carbon atoms. This is kind of amazing. You can actually pick up a sheet of atoms and hold it in your hands, which we would never have thought, say, when I was in high school, would be possible. And if you look at the electronic structure, it has electrons that look a lot like those in the topological insulator surface, except that there are 4 copies of it. So the topological insulator surface state is 1/4 of graphene. If you measure the quantum Hall effect in graphene, it looks very different from what I showed before. This was actually one of the smoking guns that led to the 2010 Nobel Prize going to graphene. Instead of seeing an integer times e squared over h, you see -10, -6, -2, 2, 6, 10. If you divide that by 4, that's a half integer times e squared over h. So this is our kind of experimental proof. There are simple theoretical arguments too, but we think that one Dirac fermion, like at the surface of a topological insulator, will have a half integer quantum Hall effect. And the reason why I wanted to explain this is the mathematics is kind of neat. So that's saying that there is a theta angle, which is basically the strength of this kind of magnetoelectric effect in a solid. You can measure it as a response to an electric or magnetic field. The mathematics that's kind of neat is that this is computed by the integral of the Chern-Simons form of the non-abelian Berry phase of the electrons. So in other words, on this slide, I've got two different connections. The one that's not scripted is the U1 ordinary electromagnetism that we learn about in our first course in physics. The scripted one is the non-abelian version of the Berry phase I talked about. And this is saying that that non-abelian Berry phase is actually measurable. The Chern-Simons form from the non-abelian Berry phase tells me something I can go measure in the lab about the magnetoelectric effect. And this is not just true in topological insulators. Actually, every material that has a magnetoelectric effect, this is part of the answer. The full answer is a little bit complicated, but as far as I know, this is so far the only case where the non-abelian part of the Berry connection matters. So I thought I'd mention quickly.
Effect comes from this Chern-Simons?
So the fractional Hall effect comes from something more complicated that we don't yet have a three-dimensional version of. But you can have a fractional value of theta. So if I break the symmetries, then yes. But then it gets a bit more complicated. So this is the full answer in any material. There are two parts. The magic thing is if I have symmetry that kills this part, the ordinary part, and it quantizes the Chern-Simons part. If I don't have symmetry, then both parts are present and the Chern-Simons part is not quantized. Basically, let me explain one quick thing about how this works. It might look a little bit odd to write something that's a little bit gauge dependent and get out the theta angle. Well, the reason why we write theta as an angle is that it's basically periodic with period 2 pi. The way that works on the right-hand side is that the Chern-Simons form changes under large gauge transformations. So this is non-abelian. What I mean is that the gauge group is U2 or U3 or something like that. Those have non-trivial pi 3s. I guess each one of those has a pi 3 that's an integer. At least there is an integer in the pi 3. I think it's probably the whole pi 3. Anyway, that means if I make a non-trivial gauge transformation, that is the shift of the right-hand side that corresponds to theta goes to theta plus 2 pi. Then you can kind of see what's magic about theta equal to pi. Symmetry forces theta equal to minus theta. 0 is equal to minus 0, but pi is also equal to minus pi, and those are the only two possibilities. So if you've got something that is periodic and odd under a symmetry, that's a natural way to get a Z2. So that's kind of how that comes out of this formula, which, yeah, so far this has only been computed in a couple of non-topological materials, but it seems to work. So I think I want to close with something that's kind of a newer discovery in the last couple of years, which is about metals. And this is a chance to give a little bit of intuition for what the Berry phase means. So I think in order to get through a little bit about the new kinds of fermions that people are looking for, I'm going to not explain too many of the equations, but try to give a few pictures. So if I just take that Berry phase I defined before for my electrons in a crystal, what is the simplest thing it governs? It's actually electric polarization, which is something about where the electrons are sitting within the unit cell. Are they sitting more to the left or to the right in the simple picture? So that means that various things I can measure, so for example, electric polarization or some optical properties or whatever, are controlled by these Berry phase objects, and actually something more recently that we realized is important called the orbital moment. And I do want to get to that because this is something where we would love any mathematical help with this object. Basically, the gauge fields, that's kind of a more standard object where physicists and mathematicians have been talking back and forth since Hermann Weyl. The new thing, we don't quite know what it means mathematically. So there are various effects in metals that come from the Berry phase. This has sort of been known for a while, but what we didn't know was, are there any cases where you get something that's kind of quantized or topologically interesting in a metal? It was thought that in metals, you could get things that were geometric, and they might involve F, but they wouldn't involve integrals of F, say, over a closed manifold, which would quantize it. But that turns out not to be quite right, and if time permits, I'll get to one. So this is just an example of one of the non-quantized things that people used to measure. There are various other things and so on, but the main thing that we think can be related to quantized properties is something in linear optical measurements. And this was motivated by the cuprates, which are our most bizarre and perplexing family of high-temperature superconductors. Since I think I only have about 7 minutes, I'm going to skip the physics motivation, but there's a reason why people care about this in the cuprates. So now let me say, what are the new metals that we have, and how does that relate to the Berry phase? And that's probably a good note to end on. So I mentioned before, in the old days, we had diamond and we had graphite, and graphite is kind of a layered bunch of two-dimensional carbon sheets. The more recent progress is making lower dimensional versions, so you can make a sphere of carbon, you can make a tube of carbon, and most recently, and most spectacularly, as far as physics consequences, you can make a sheet of carbon. That was originally done by taking Scotch tape and pulling sheets out of a lead pencil, basically. We have more sophisticated ways now, but that's how you can win a Nobel Prize, if you have the right Scotch tape and you're persistent enough. So there are neat optical properties that graphene has, just to kind of give a sense for why this might be interesting. So as I mentioned, you can pick up a sheet of atoms that's an atom thick. That's kind of cool. And if you look at the sheet of atoms, you realize that it's not quite transparent. To be precise, it attenuates about, or it doesn't transmit about 2.3% of the light. And that number 2.3% is just pi times the fine structure constant, E squared over hc. So this is another example, basically, where fundamental constants are showing up, nothing particularly material dependent. And in this case, it's a metal. It's not an insulator. So graphene has, it's kind of a semi-metal, to be precise. It has that E versus K linear that I showed earlier in the context of topological surface states. So we'd kind of like to understand, are there other neat things like this that happen in metals? And in particular, I'll skip that. So we now have lots more two-dimensional electron gases than we used to. This is the two-dimensional topological insulator surface. This is graphene. The way the quantum Hall effect was discovered, if you're curious, was heterojunctions between two different semiconductors. Anyway, so here's a way to state it in terms of Institute for Advanced Study terms about what happened in the last couple of years. So graphene, aside from being very important from kind of a structural point of view, it had this remarkable electronic property that was it was the first case of a simple material with massless electrons. How can you generalize that to three-dimensional materials? We would love to find three-dimensional versions of graphene, and in the last couple of years we have. So the standard description of three-dimensional electrons, like the particles that appear in particle physics, for example, are so-called Dirac equations, Dirac particles. They're described by the Dirac equation, which is a 4x4 matrix equation. Something that Hermann Weyl figured out was there are actually two different ways. One standard way to take half of the Dirac equation and make it an equation of 2x2 matrices was figured out by Weyl. It basically describes particles that only have one-handedness. So the Dirac equation has massive particles that if I transform, the particle can go from left-handed to right-handed. The Weyl equation will describe massless particles that have a handedness. It was hoped for a while that neutrinos were actually Weyl particles, but now we know that they're not. They're Dirac particles, same as everything else. So there do not seem to be Weyl fermions anywhere in the standard model of particle physics, but they do exist as the low-energy excitations of some new materials. Tantalum arsenide, just figured out in the last year or so. And this actually has kind of a topological interpretation in terms of the same Chern number we talked about before. And I can also explain how this connects to the experimental discovery. So if I take a Dirac point in a three-dimensional material, let's say I found one, if I break time reversal or inversion, that splits into two of these Weyl points. The Weyl points have a topological charge in that if I make a little sphere around them, the Chern number on that sphere is quantized, let's say +1 and -1 in the simplest case. And what led to the experimental discovery was a prediction by my Berkeley colleague Ashwin Vishwanath and collaborators that at the surface of one of these, there will be kind of a metallic line of states connecting these 2 points in the surface Brillouin zone at the projection of these. So it's a little complicated, but it's kind of similar to topological insulators. There's something you can look at the surface in photo emission that would tell you that you'd factorized your Dirac point into Weyl points, and that's what they were able to do. So this is all brand new, and we're trying to figure out what are the physical consequences of these new three-dimensional massless electron materials, maybe related to this topology, maybe related to something else. Here's an example of something topological that actually gives a negative result, and the most recent thing we did was try to figure out a positive result using something similar. So it was thought for a while that if you took one of these Weyl materials, if you apply a magnetic field, you will get a current along the magnetic field. And that was exciting because it violated things that we thought we knew from the early days of solids. It turns out that it's wrong if you do the topology right, at least in equilibrium. If you look for this so-called chiral magnetic effect, so omega is what I called F before. It's the Berry curvature. And V is the ordinary velocity. And people kind of focused on this term. And if you think about all the terms carefully, you get this product. It's basically Berry curvature dot group velocity. And it turns out that if you add all these up, indeed you get 0 as kind of a topological property in any metal. So this is saying, abstracting a bit, that The reason why the chiral magnetic effect is actually 0, why when you apply a magnetic field you don't just get a current along the magnetic field, is because of this little topological tracelessness identity, which is pretty quick to derive. You can move it to the surface and get the outward directed Chern number on the surface, and if you add those up for all the Fermi surfaces, you get 0. So it's essentially undergraduate calculus and kind of fancy language. So I think what I wanted to close with, I mean, we have the thing that I would love to understand, it turns out that there is something related to that chiral magnetic effect that is non-zero, and it depends on the orbital moment of Bloch electrons, which is very much like the Berry phase, sandwich in it an additional Hamiltonian operator. So it's some combination of the Berry phase of a fiber bundle and one more operator. And if anyone's ever heard about anything about that mathematically, I would love to understand it. With a lot of work, you can show that it's physically predictive. So this is the thing that if there are, I'm sure that there are many card-carrying mathematicians in the audience. If you've ever seen something like this, then corral me afterward and tell me what it's called so I can learn more about it. But we found out that it's physical, et cetera. So that, the last thing I think I will end on, and this is just 2 slides because I'm out of time, is the other way of taking half of the Dirac equation is maybe the big holy grail in physics right now, which is a so-called Majorana fermion. So Weyl fermions you make from the Dirac equation by fixing the handedness. What Majorana did is a bit deeper. In Dirac equation, the most dramatic prediction of that was that the electron had an antiparticle called the positron, which has the same mass but opposite charge. But you could have, so this is symmetric theory of the electron and positron, you could imagine a situation where a particle is the same thing as its antiparticle, and we still think that might be the case for the neutrino. We don't actually know if this is true. There are big experiments underway. It turns out we can make these things, we think, in condensed matter physics in some of those superconducting classes of the tenfold way that I didn't actually talk about, and that's why we're so focused on trying to find examples of the superconducting classes in the tenfold way, because they would support emergent particles that are Majorana fermions. And my last slide, the deepest fact about those Majorana fermions is that they're a counterexample, at least the Majorana fermions that happen in condensed matter. This is not true for the ones in particle physics, but the Majorana fermions that happen in condensed matter are a counterexample to the main thing I used earlier, what I think is the most fundamental thing in undergraduate physics, which is that particles are either fermions or bosons. They're either half-integer spin fermions, which behave one way, or they're integer spin bosons, which behave the other way. Basically, the difference between these on a fundamental level is that if I exchange fermions, I get a minus sign, and if I exchange bosons, I get a +1. If I exchange these emergent Majorana fermions in condensed matter, I don't get a -1 or a +1. I get some more complicated representation of the braid group. This is what, in case you wonder what Mike Friedman has been doing for 10 years or so, it's this. It's representations of the braid group applied to condensed matter physics. And we're much closer than we were 10 years ago to actually finding examples of this, in that there are now published papers in Nature and Science, although they aren't that convincing. But we think we're getting close to realizing particles that would be neither fermions nor bosons in an even more interesting way than the kind of abelions we get in the fractional quantum Hall effect, which I will skip. So there were a lot of things in the talk. It wound up being kind of an introduction to topology in solids at the moment, but I hope that I've at least conveyed that there's a lot of stuff in the last 8 to 10 years. And the main point I would make is somehow at least certain kinds of topology wind up not just being useful, but actually being essential if you want to understand a surprising variety of things in solids. That could be topological phases. It could be simple things like electric polarization, magnetoelectric effect, optical effects, which is what this circular photogalvanic effect is. And then, yeah, even deeper things like the existence of Majorana fermions and so on. So all of a sudden, there's a line I sometimes quote in The First Circle, probably the best book about topologists that I know, by Solzhenitsyn, that topology is great, but it will never have anything to do with anything. And obviously, we know many cases in this workshop that that's not true, and this is the case in my field. So better stop.